Hello, I'm Andrew. This video is for iOS developers, and in it I'm going to show you how to build a Bluetooth service layer in Swift using a state machine pattern. This topic has been taken from a section of an online course that I developed, the complete Bluetooth IoT design course for iOS, which takes students through a complete front-to-back design and build of a Bluetooth-enabled LED lighting controller. You can find out more information about the full course at the end of this video. In this video, I'll be focusing on that layer of code that sits between the application proper and the iOS Bluetooth framework, or Core Bluetooth as it is called. Here is a diagram of the application architecture, a straightforward MVC style application, and it is this component on the left, BLE Service, that we're going to be looking at. BLE Service presents an API to the upstream application, read, write, set, notify, etc., and handles all of the interaction with the Core Bluetooth that is needed to fulfill an API call. BLE Service also publishes out the results of the API calls along with status updates. BLE Service has been designed following a state machine pattern, and there are a number of features of the Swift language that lend themselves nicely to implementing state machines. Now, one of the questions you might already have is, why do I need a service layer? Why do I need a state machine? Isn't this just overcomplicating the design? After all, Core Bluetooth is so easy, right? Yep. Well, my own personal experience is correct. It is easy to get something up and running fairly quickly. But getting from that something to production-grade code, well, that takes a little bit more thought. Let's take a look at exactly what we have to do at that Core Bluetooth interface. Here is a diagram of the service layer sitting between the upstream application proper and the downstream Core Bluetooth framework. There are a number of asynchronous events being handled by a set of functions that I'm calling event handlers. There are events coming in from the UI based on user actions. There are events originating in Core Bluetooth and in timers. The event handlers, a collection of API functions and callbacks, in turn initiate some action by invoking an action handler. The action handlers perform whatever task is assigned to them, but typically it will involve making Core Bluetooth API calls and/or starting-stopping timers. Each event and the action that it invokes must be handled serially. It must not be possible for one event to invoke an action while a prior event is still being processed. So we need a queue sitting between the event and action handlers. Now we can see that the state machine is in fact a little piece of machinery that takes an event from the queue as input, decides what action to take based on the current state, and then transitions to a new state in readiness for the next event. So what about the timers? What are they for? Consider three cases. 1. The user starts the application. An action handler is called that tells Core Bluetooth to start scanning for peripherals. Maybe Core Bluetooth discovers a peripheral and reports that back to the application, but maybe it doesn't discover any peripherals. There is no timeout built into Core Bluetooth that tells it to stop scanning after some amount of time. So we need a timer to provide that timeout. When the timer fires, we stop scanning. Now we have a race condition, in that Core Bluetooth might have discovered a peripheral just at the same moment that we told it to stop. So we have to be able to handle the case where we get a did discover peripheral event after we have told Core Bluetooth to stop scanning. More generally, we have to be able to handle any event in any order, regardless of what is currently going on. Case number 2. If we do discover a peripheral, we're going to want to connect to it. Most of the time, a connection will complete successfully. But what if it didn't? We have to consider the case where a peripheral goes out of range or is switched off just around the time that we discovered it. When you tell Core Bluetooth to connect to a device, it will attempt to do that forever. If you don't stop it, you could find Core Bluetooth reporting a successful connect a week later, or a month later, or whenever. So we need another timer to control how long we are going to let Core Bluetooth try to connect to a peripheral. And third, finally, consider battery drain. If we do connect successfully to a peripheral, that connection will be maintained forever, unless we tell Core Bluetooth to disconnect. A connection is in reality a continuous exchange of messages between two devices. If this goes on forever, the batteries on both devices will be drained. So we need to disconnect after a certain period of no user activity. Let's add another timer to control this timeout period. Okay, so that's the timers. One last issue concerns how to handle inbound API calls from the UI. Consider a case where the user performs some action to read the value of a characteristic. The set of actions that need to occur because of this are listed in the table. First, we need to connect to the peripheral. If that proceeds okay, we then need to discover the service that contains the characteristic. If that proceeds okay, we then have to discover the characteristic. If that proceeds okay, we can then read the characteristic. And Core Bluetooth will then respond back later with the characteristic value. So all of these actions need to complete before starting to process another UI event, if there is one. To ensure that this is the case, we have to add another queue. If that sounds like a lot of work every time you want to read or write a characteristic, then it's good to know that, for bonded devices, Core Bluetooth caches the services and characteristics, so repeated discoveries do not cause over-the-air activity. Only the read characteristic action actually goes over the air. Bonding is not covered further in this video. So that's it for what we need to do in the service layer, and a state machine approach will help us guarantee that we have a mechanism in place for handling every possible event for every possible condition. Of course, we still need to make sure that we do something sensible in every situation. So how do we code up a state machine in Swift? There's quite a few examples out there on the internet, and these two in particular are really good. Both of these influenced the way I designed the state machine for the online course. You can build a state machine as a set of nested case statements, but I prefer a table-driven approach. I find it easier to correlate the state tables with the state diagrams. And yes, you do have to draw state diagrams, except for the most trivial cases. The other feature I wanted to incorporate is state on entry and state on exit actions, as I've historically found in the past that can lead to fewer states overall in your design. Let's take a look at how this would work. Here is the basic flow. The state machine takes an event off of the queue and performs a table lookup to decide what actions to perform. First, in the context of the current state, the machine checks that the state action table to see if there is an on-exit action to perform. It then checks the action table to see what transition actions to perform and what the next state will be. After performing the transition actions, the machine switches the current state to the new state and checks the state action table again, this time for any on-entry action to perform. The machine then loops back to process the next event on the queue, if there is one. There is also an error table, not shown in the diagram, that tells the machine what to do if an error occurs during the execution of an action. The tables shown in the diagram are a logical representation, In reality, I'm using Swift dictionaries as opposed to Swift arrays. Swift dictionaries have a very similar performance to straight array indexing, so using dictionaries helps save space and provides a built-in mechanism for handling null or invalid actions. The action table typically has very few entries. In array terms, it would be called a sparse array. Using a dictionary, we only need entries for legitimate combinations of state and event. Going quickly through the tables, the state action map has an entry for any state where either an on entry or an on exit action or both is required. Where there is an entry, the value in the map is a Swift tuple containing two functions, each of them optional. For the error action map, there is a mandatory entry for every state. The map entries are also tuples containing an optional function and a non-optional next state. The action map is a two-level dictionary, a dictionary of dictionaries. At the outer level, there is a mandatory entry for every state, and the value of each entry is another dictionary. The second level dictionary contains an entry for every valid event for that state. Lack of an entry for a given event indicates an invalid event for that state. So that covers the high-level description of the design. Let's now jump into the code and look at the detail of the implementation. We'll be paying specific attention to any Swift language features that we're drawing on to help us with this design. So let's go over to Xcode and let's take a look. Okay, so here we are in Xcode and we are in this BLE service.swift file, and in this file we've got two classes that are declared. The first is a BLE service class, and the second one is a machine class. Here we go, class machine. We're going to look at the code for the machine class first, and then go back and take a look at the data structures that drive the state machine. So here we are in the machine class, and there's 4 instance variables, 3 state maps or action maps, state maps, and a current state. Initialization function takes these maps as input, so we're actually initializing the maps in BLE service class and passing them into the machine here. And there's only 2 functions in the machine class. That's this one, which is an nil state error, is an error handler. And the second function is this one, handle event. And this is the key function for the state machine. Everything happens within this function. Now, this function gets called every time iOS dequeues an object off of the queue. And remember that the queue I'm talking about is the one that sits between the event handlers and the action handlers. And the queue type that we use is an iOS dispatch queue, and the objects that we put on that queue are Swift closures. Now, if you're not fully familiar with Swift closures, they're conceptually very similar to blocks in C or lambdas in other languages. And they're little snippets of code with enclosed state. And you can pass these things around, assign them to variables. And what we're doing is we're putting them on a queue. Every time iOS dequeues that closure off of the queue, it ends up executing the function, which in our case is this function here, handle event. So within handle event, we are, first of all, we're checking to make sure that we're not already executing an event. As I mentioned before, we mustn't do 2 at the same time. We've got to complete one event before we go back and pull the other one in. And here is where we're checking to make sure we're not doing that. Now, technically speaking, with the queuing system, this should never occur, but it's in there. So this is a just an extra little bit of extra safety, if you want to call it, an extra layer of safety. The next thing we do here is we check to see if the event is a valid event for the state. If it's not, we throw an error, and if it is, it correctly returns the transition actions for this event state combination. And given we've got the transition actions, we then go and execute. First of all, we look to see if there's an on-exit event to execute, and if there is, we execute it. Next, we execute this for each. We'll execute an array of transition actions, if there are any. And finally, we look to see if there's an on-entry action to execute, and if there is, we execute that. And that's it. That's the state machine code. So not a lot to it. And it's really all the data that drives everything. So there's not much code, but there's quite a lot of data. Now, all of the actions, I mentioned this earlier as well, all of the actions that get invoked could potentially there could be an error in that code processing. So we want to trap on that and do something about it. So we've got it all wrapped up in a try catch block. And the way you do that in Swift, obviously, is it's actually a do try and then catch at the end. If there's any application error in the action handlers, it will throw it into this error handler here. Yeah, so that's it. That's all there is to the state machine from a code perspective. We're now going to go and take a look at the data structures that drive the overall behavior. And first, the implementation of event and state and how the state maps are set up. So let's move up a little bit, up here. Actually, we're going to do state first. Let's look at state first. Here we go. Now, bState is Swift enum. It's got a type of int, and we've made it conform to this case iterable protocol. I'll explain this in a minute. It's really important. Just bear that in mind, case iterable, and we'll come back and explain why we're doing that in just a moment. This extension to bState just provides a readable text string for each state. So rather than getting some funny number, you get you can get a textual output. This is for debugging, logging things in the log files so you can see what's going on. Next, we've got the event. Again, bEvent is Swift enum. A little bit more complicated because here we've got three of the cases with this little parameter stuck on the end. And putting a parameter on the end like this is called an associated value. And it's a way in Swift where you can attach a blob of data to a case instance. And you can then access that data at the point where you resolve that case instance. So we're using this to be able to pass through the discovered peripheral, the discovered service, and the discovered characteristic. As we discover them, we pass them through from the event handlers through to the action handlers using this technique. So payload, P peripheral, is just the peripheral, that's it. And PS, peripheral and service payload, PSC payload, peripheral service characteristic. So you can see that we can actually attach arbitrary blobs of data to each case statement. We're only attaching blobs of data to 3 of them, and they're different blobs, but that's okay. They don't need to be the same type of, or data type that you attach as associated values. Now, one of the, again, we've got an extension that gives us a textual string, but one of the complications with associated values is that the compiler can no longer create a unique hash code for each of these enums. So we have to force conformance to the hashable protocol. Here, we're doing that. That's what all of this does. And we force it by using this hasher function that takes a base hash value provided by the compiler and combines it with a unique value that we provide, 0, 1 through to 25, to create a unique hash. Now, the reason we have to do that is, and the reason why the compiler can't create a unique hash itself, is because these associated values themselves are not hashable. We're just passing structures. We're attaching a structure blob to these cases, and structures are not hashable. If the associated value was, for example, an int or a string, int and string themselves are hashable, so the compiler would have no problem figuring out a unique hash for each of these cases. But because our blobs of data, our associated values, are not hashable in their own right, we have to do this. So a little bit more complicated. Maybe at some future version of Swift, they'll have found a way to be able to do this automatically as well. Okay, so let's now go to the state maps, and to help us with more readable code, I've defined 3 type aliases here. So this is type alias introduces a new type into the system, and I'm creating or declaring 3 new types: a state action map type, an action map type, and an error map type. And for example, the state action map type is declared as being a dictionary with a B state as the key and a tuple as the value. And that tuple has 2 functions, an onEntry function and an onExit function. Each of those functions takes 3 parameters, event state and optional string, and they both can throw. So that's now condensed it. We can just deal with state action map type now. It's going to clean up the code further up, as we'll see. And we've done the same thing with action map. Action map is a dictionary of dictionaries, and it takes a state plus a dictionary as a state as the key and another dictionary as the value. So that's the type aliases. If we now go up to BLE service and we take a look at the declaration of the instance variables within BLE service, we've got these 3 maps again that we initialize here to default safety values. So again, state action map is of type state action map, and here we're initializing the type. It's a dictionary, as we know. So we're initializing the dictionary with a key value pair, and this is where the case iterable protocol is important. bstate.allCases yields a list of all of the cases that have been declared for bstate. The compiler figures that out. We don't have to figure it out. So with that list, we then map it using this higher order map function to a second list, and the second list is a name value pair. Or key value pair, you can call it. The key is an instance of the case, and the value is a tuple with 0,0 in it. So the takeaway for this really is that by using this all cases structure, or not structure, protocol, we guarantee that we're initializing this dictionary with an entry for every possible state that we've got declared. And as I say, the compiler is doing that for us. We don't have to worry about jiggling around with tables every time we add or subtract a state. It's taken care of automatically for us, which is a good thing. The second thing is then that the values that are associated or applied with during initialization time is for every state. For this particular state action map, we give it a nil-nil tuple, so it will do nothing. And that's actually what we want it to do. So there's always a valid action for every state, even if that action is do nothing. And later on we update the state action map we overwrite these default values with meaningful values so that it does what we want it to do. The same, everything I've just said applies to action map and error map, but just one last thing to point out. For action map, we're initializing the dictionary with the key is an instance of state case, B state, and the value is an empty dictionary. So with that initialization, what it means is that every event for every state will throw an invalid event for state error. Everything will error. And that's actually what we want. What we then do, obviously, is we come back and we update this table, this map, with valid values. But it does mean that if we ever get an invalid value, we're guaranteed to throw ourselves into the error handler. It's not possible for a particular event, for a particular state to flip through unnoticed without doing anything. Okay, and then finally, the setup state maps itself. This function is the function where we overwrite and update particular rows in each of those maps to get it to do what we really want it to do. And here we can see the state action map. We are putting in legitimate values for these 7 states. And each one of them has got a function to perform, and it just so happens for on entry, they've all got an on entry action to perform. None of them actually have an on exit action, which is fine. The action map itself down here, and you can kind of follow this through to see what's going on. But for the online state, we're saying there are 4 valid events for the online state, and one event is the online event itself. That could happen. And scan, retrieve, and offline. Anything else in the online, any other event that we get in the online state is going to throw an invalid event for state error. And each of these entries now has a valid action to perform, and 3 of the 4 have a next state to go to after that action has been performed. The online state stays in the same state. If it gets another online event coming in, it just sits in the same state. It does notify out to the upper application, but it doesn't do anything more than that. So that's that. Down here, look, here's an example. We're in the scanning state and we get a scan success event coming in. And here is a case where we actually do 2 actions. We send out it's actually 2 notifications. We tell the upstream that we successfully scanned, we found something, and along with that message will be the peripheral that we've discovered that can then be displayed on the screen. And we also tell upstream that, okay, we're now ready to do real work and the next stage. So that's a case of more than one action being performed. Also, in quite a few places, you'll find a perform null action as the action, and perform null action doesn't do anything other than log to your log file. So I've put a perform null action in anywhere where we don't actually have a concrete thing to do, concrete piece of work to do. So we can always track and trace exactly what the state machine is doing. And this is particularly useful during early development and coding. You want to see everything that's going on. But, once you've got everything up and running and working, you could replace this perform null action with nil. Now, one other point to bring out, if you look at the definition of all of the action handlers, they all take state, event, and an optional string. And it's important to point out the state and the event are being passed into the action handlers only for debugging and logging. You should not be testing the values of those two items in your action handler. If state is equal to this, do that, etc. The whole point of a state machine is you don't need that type of code. So if you do find yourself writing case statements in your action handlers or, if-then statements in your action handlers, something's wrong. You got your state machine set up wrong. The whole point of the state machine is you don't do that. The state machine makes those decisions for you. So just be aware of that. Now, the only other thing to point out is making sure that the state maps here have the correct entries. It can be tedious. And so to help, I always draw state diagrams and I use them to cross-check against the map entries here. Here, for example, is the state diagram for the first half of the state machine. And here is the state diagram for the second half. And I've just left the little green check marks in there. That's what I do to cross-check that the way the state machine should work is actually reflected in the map tables. I've actually got an entry in the map table for each of those transition lines. So that's how I do it. And yeah, it would be nice one day if there was a tool that would generate the data maps, the state maps, automatically from a diagram, but that's a thing for the future. Alright, so there we have it. In this video, I've covered why a state machine pattern is a good choice for handling core Bluetooth activity and how to implement one in Swift. As mentioned previously, this topic has been taken from an online course that I developed, the complete Bluetooth IoT design course for iOS. If you have any interest in discovering more about the full course, you can find it here on udemy.com. Just search for Bluetooth and it is this course here. You can also subscribe to this YouTube channel. I will be putting out more information on Bluetooth topics and real-time operating systems. So by subscribing, you'll get an update as soon as I put any new content out there. Other than that, best wishes with your work. Remember to stay safe, and I hope to see you again on the inside. Take care.